Okay, I will try to explain the package that I made for playing with Turtlesim. Here, right now, we have these files, but later I will be updating the README and adding a little bit of maybe two or three images to view what is Turtlesim, what is doing. But basically, this is the repository. This is the package. Those are the package files. Uh, and we have two folders here. One is for the launch file, and one is the source of the application. Just to check what's inside the folder, it's only there are two launch files, but the one that we are interested in is this one, the Turtlesim Buster, and the source file only this one, moveturtle.cpp. The other ones are examples. If you want to play with publisher and subscribers, but the application just only uses the moveturtle.cpp. And anyway, there is a package.xml explaining or have the dependencies that needs to run the to run with the package and the segment list. Let's explore it by first. You have to have CMake minimum required version of 3.02. The project is named Turtlesim Buster, and those are the package that we are using, only raw CPP and standard message. And also we need to include the directories, and if you want to build all the applications, you include one executable at a time. For this example, we can delete these ones, the talker and the listener, and we can keep the move turtle that we are interested. So that's the first part for executing the files. Another thing that we are interested to see is the construction of the package XML. The package XML just contain information about the package, the name, the version, a little bit of the description, the maintainer, the license, and also here the interesting part is that when we build the Rust package, we decide with which dependencies we can run the package, Kakin, RustCP, and standard message. The launch file is to run Rust core, Turtlesim node, and spawn and launch the the move turtle file. So here you see that this is the node name only. It's a default name. You can put anything for everyone. The package is named Turtlesim, and the node is named Turtlesim node. And we want to view the output on the screen. Next, to run our application with Turtlesim, the node, we also are launching the application that is named as the package name is Turtlesim Buster, and the type is Turtle. So those are the files related. Now, with everything explained, the launch file, the CMake list, the package, we can view the application, the moveturtle.cpp. Here, I'm including all the necessary header files for running ROS, message, and mathematical operations. In example, we need ROS because it is the default package. We also are using only two messages, the twist message and the post message, all from geometry messages. And also we need the pose of the Turtlesim simulator. We will spawn turtles and we will kill turtles. Finally, I'm doing a PID controller for distance and angle, so we need mathematical operations for Arctan 2. Here I'm only using namespaces for the standard operations. I create here some variables, one for the post to the public or global, the publisher for the command velocity, and the subscriber, that is the post sub. Also, we need, I'm using services, not actions. So we need an action to spawn an action client, a service client to spawn a turtle, but this service also needs a request and a response. That's the limitation of services. We need a request and also a response, and also with services, we need to wait until the operation completes or not. So for each service client, we need a request and a response. And the same for the kill client, we need a request and a response. Those are the implemented functions. This is the callback function you will see later to implement passing to the Turtlesim post. So in this callback are functions that run asynchronously. They are called by the interrupt system and pass information, and we can do anything with that information. So the Turtlesim will give us the post, and we are storing it on a variable each time that it is running the application. This part of this function, is trying to move the turtle. We need to define a goalpost and a tolerance that is the minimal distance that we decide what is achieved. For example, if we want 5 meters per, of distance, and we put a tolerance of 0.1, or goal will be up to 4.9 meters, and we'll decide to stop moving the turtle here. This is a PID model for distance. How do we put the control signal? We need to make a PID, or at least I made it in that way. We don't need PID, we can just only use P controls, but I decided to use a PID for distance. We need also a PID model for the angle, or I did a PID model for the angle. This function is to spawn a leader turtle, the turtle that will appear anywhere in the field at a random position. This will be the leader because the current turtle will try to follow the turtle. And this is the kill function for the uh, for obviously kill a turtle that is being spawned. And here is the main application. It's pretty simple. If you do all the functions. So first we start rows. It's mandatory to start rows with rows in it. Next we define a node handle that will have all the functions that we need. And this is for the velocity command. We are using geometry message and the twist message exactly. And we will advertise this command or publish this command. And the buffer size is 10. Also, we try to subscribe to the post command. To the post topic. Those are topics. To the post topic, we have a little buffer of 10, and for every time the application will be running, we go to the post callback. So later I will explain what is the post callback. Also, we have two services, one for responding the turtle and the other one for killing the turtle. Here is a local variable, the goalpost, and we will make it random positions between the square, between 0 and 12. That This is the micro world of the Turtlesim. Next, we will spawn a turtle and a goalpost exposed here at a random position, and try to move the turtle, the current turtle that is by default in the field at that goalpost, but with reached distance of difference in the distance of 0.1. And then finally we will kill the turtle and repeat the process again and again and again. So next, what are inside those functions? Well, to move the turtle, we need the final pose and the tolerance, that is the minimal distance. We're using geometric message, and we'll try to do a loop rate of 10 Hz. That's pretty enough to do the application. Here I create a vector of the uh, variables of the PID, KP, KI, and KD for distance and for angle. So next I make a request to see which is this control signal that we can apply to the PID, and we also get the pose and the goal pose is the finish pose and our current turtle pose. I hard coded that part is the time difference or the rate in the PID application, but the right thing to do is to view how much rate is executing right now in the topic, and you can put it here. But I try to be a little bit practical and just put it as it is. So this is the delta time. Next, we pass the control signal to the linear velocity. Also, we implemented a PID for angle. Those are the variables for the angle. And finally, we obviously pass the finish pose, pass the theta, and also the turtle pose. And actually, we can pass the delta time, I mean. And finally, we publish those variables to the command velocity. We also spin once, try to sleep to fulfill the rate, and repeat all the process until the tolerance is reached. Next, because we want to cause the turtle bot, we need to send the linear and angular velocity to 0 and publish that message. Here, the post callback. Did you remember the lines above? That here, where? Okay, here. When we try to subscribe to the Turtle One post, it will launch every rate post callback. This post callback is right here below, and we are trying to get the information of the pose of the current turtle that is moving. We'll try to put it on that global variable that is up below, up or above. Here it is. Yes, there is the variable. But you can do it manually. You can do it. It is the same as turtle post.theta equals post message and the pointer to theta, the same to x, the same to y, the same to z. Also, here are the calculations for the PID. For the PID, we have to retain the previous error for the derivative and derivative gain. We also have a local variable named error to calculate the error, and retrieve all the parameters of the KA's vector. That is, those are the parameters for the PID. Next, we calculate the difference of the current pose of the desired, so the current x, desired x to the turtle pose, the same by y, and make the magnitude of the error to store on the function of the PID controller. So the control signal will be a proportional gain multiplied by the error plus an integral gain multiplied by the error by a difference of time, and the uh, differential gain that will try to compensate the error of the integral controller. So here is pretty simple. And finally, obviously, we have to retain the current error for the controller. Also, the same is repeated here for the PID of the angle. We get the theta error by calculating the difference uh, of the pose of the set point pose and the current tutorial pose divided by the set pose of S. It's the tangent formula, and the difference of this uh, angle and the turtle pose angle will give us an error angle. Anyway, we can apply again the control signal by calculating the PID and retain the previous theta error to make the PID calculations again. Finally, this function is to expand any turtle. We again take the pose. I call it the leader pose to the turtle that appears in the field at random positions. So because we have the created spawn request, we need to pass the x position, the y position, the z position, and the name of the turtle, the new turtle. I name it leader. Finally, we will wait for the service a little bit. We call the service, and we'll wait a little bit. And if the operation when the call is succeed, if it succeeds, we will display on the output the name of the turtle. Finally, we try to repeat the name, the same thing, to the current turtle that is created. But though, as you remember, we kill the turtle when we finish to move the turtle. Yeah. First we get the goal position, then spawn a new turtle, then move the new turtle, and kill the turtle. So that's the final part. We kill the turtle by requesting the name of the spawned turtle, wait for the field service when we call, and if we succeed, we kill the turtle. So that's basically the application, explaining all parts of the code. If you want to view the application running, I have a separate video about the thing about the new spawned turtles. But let's play to see what is happening. Okay, here I make the package. So for making the package, we need to be on the ROS workspace or the testing workspace. Depends on what kind of workspace you name it. And when we build the package, we see here that we have the move turtle, the talker, the listener build. Next, we can then do a ROS launch for the package name that is Turtlesim Buster and the launch file that is Turtlesim Buster launch. Let's see. Okay, and this is practically what it's doing. It's trying to follow the new spawned turtle. It will repeat forever. So if you try to accommodate the values of the PID controller, of course it will be faster. That's why I'm trying to explain here to you. I'm here and changing the values of the PID controllers for this and angle. But obviously, if you do that, because the application is not tuned for optimal control, you will see that the turtle sometimes will try to reach the point, but it will oscillate. So you see, it goes faster, but for some situations like this, you will see that the controller keeps oscillating until it's stabilized. So it's a good application to start uh, running with ROS and also trying to understand PID control, also publishers, subscribers, and so on. So practically that's all what I did. If you want to visit the repository, it's this one, and that's all. Hope you like.